All right, everybody, I'm doing the NHT 2025 chemistry exam. Hopefully it's not too bad. Okay, cool. Below is the nutritional information. Energy available to 100 grams. This is also per 100 grams, so it makes our life super easy. I believe this is 16, this is 17, and I think this is 37. So you just refer to that in your data book. Sorry, in the data book. Oh man. Okay, it's somewhere. Oh yeah, here, 37, 17, 16, right? So super easy question. So we just do these times, and we don't have to do it relative to anything because they've already given it to us. Um, they've already given it to us per 100 grams. So they've made our lives super, super easy. So 17.8, 17 times 8.9 plus 37 times 5.2 plus 78.5 times 16. 1599.7. So that's 1600 kilojoules. This is probably that one. Cool. 1 mole of C612. Generally speak, or do we have to, is there any easier way we can do this? There probably is. Oh yeah, the easy way we can do this. I'm trying to think. There's the easiest way to do this is to basically, so during cellular respiration, the oxidation of 1 mole of glucose produces basically how many electrons. The easiest way to do this is to figure out the oxidation numbers when in glucose and in carbon dioxide, right? So obviously in carbon dioxide, it's its most oxidized form, right? So that's when glucose has been fully oxidized, right? To +4. When we're trying to figure out the oxidation number of carbon in glucose, we just need to do 6x plus 12 minus 12 equals to 0. So x equals to 0. So we're actually losing 4 electrons. Okay. So 0 is going to +4, right? However, that would be the case if we were only dealing with 1 carbon. We're dealing with 6 carbons, which would mean it would be 6 times 4, which is 24 electrons. So it's probably the easiest way to do it. There's probably some other ways you can do it. That's the only way I kind of knew. You could also write out the entire equation, but I did not want to do that. Which is the closest to the activation energy required to produce 7 moles of SO3? So I don't think the enthalpy. Oh wait. So does the activation energy actually change? Let's see. Um, so the whilst the amount of energy released, so so here it's a bit interesting, but generally speaking, the activation energy doesn't actually change. So the enthalpy will change, but we're still dealing with the same molecule, right? So we're still dealing with the same amount of reactants, and therefore it's the same types of bonds that needed to be broken. And therefore that's not going to change the amount of energy we need to break it. So even though we're dealing with more amount of SO3 that we need to produce, so sulfur trioxide, right? We the activation energy would remain the same. So it's about 135 kilojoules, which would probably be 140 actually. So yeah, it's actually really interesting. So the enthalpy is going to change, obviously, but it would look something like that, right? So the activation energy is not going to change. Which is the closest to the amount of bioethanol required to produce 250 millijoules of energy when it is used in an engine with an efficiency of 25%. Okay, so in order to produce 250 millijoules of useful energy, we would need to overall produce 1,000 millijoules of energy, right? Because that 1,000 millijoules is then being converted with an efficiency of 25% to 250 millijoules of actually useful energy. So overall, we need to produce 1,000 millijoules of energy. And in order to produce 1,000 millijoules of energy, right, because it's 25%, so it's 250 divided by 0.25, right, which leads to that. In order to produce 1,000 millijoules of energy, we just do 1,000 divided by 30, which is like 3.3, I think, or 33. So it'd be that, right? So it'd be 4B. Yeah, so it'd be 100 divided by 3, by the way. Just like 33.33333. Cool. At equilibrium, the rate of the forward reaction is 0, so that's not true. Okay, so the rate of forward reaction is equal, okay, to the rate of the back reaction. So number one is not true. The extent of the reaction is measuring how quickly the reactants are consumed. That is rate. So neither one or two are correct. Okay. So when we reach equilibrium, for example, so this is a system that's at equilibrium. For example, let's take this to be N2. The rate at which N2 is being consumed is also the same rate at which N2 is being produced, right? So the rate of the forward reaction has to be above 0. Okay. Another equilibrium question. What change to the system occurred at time 2? So because there's no evident initial change in this situation, I'm inclined to think that it's a temperature change, which would be C. I mean B. Yeah, would it be? Yeah, cool. Because there's no change. So here, what we're doing here is we're adding N2 gas. If we added N2 gas, it'd look like this. If we removed NH3, it would look like that. If we increase the volume, then all the concentrations would drop, right? So because there's just curves that we're looking at, it would just be a change to the temperature. And I've just guessed that it's increase in temperature. The reaction quotient at Q at T1 is a quantitative measure of. So I didn't even have to look at it. This is just a definition. It tends to be just the extent of the reaction. The Kc is the equilibrium constant, but the actual extent of the reaction tends to be the reaction quotient tends to be the extent of the reaction, right? So at T1, if we figure out the QC to be blah, 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 the QC in this situation is most likely going to be different to the Kc. So it basically tells us at what direction the reaction is traveling in and, whether it's at equilibrium or not. So at a constant temperature, an increase in the reaction at equilibrium can be achieved by increasing. So, okay. So okay. So an increase in the rate of the forward reaction at a constant temperature can be achieved by increasing the pressure in the reaction vessel by adding an inert gas. No, because adding an inert gas wouldn't really affect the equilibrium of the situation, right? Because it's not part of the reaction system. So the system won't actually respond to this to the pressure increase. So B would be wrong. Equilibrium constant. So obviously that doesn't really do anything. So we increase the products, but that doesn't really do anything. It doesn't really have an impact on the rate. We're looking at the rate here. The volume of the reaction vessel. So if we increase the volume, that's actually going to decrease the concentration. So it's actually going to decrease our frequency of collisions. The concentration of the product in the reaction vessel. So that's most likely going to have an impact on our reaction rate, just because if we have more product, um, um, then we just have more stuff, right? And even if we have more product, it's going to eventually lead to more reactant, which is going to help the forward reaction. So a lot of people might not have done B because it says product, but that's okay, because even if we increase the product, it will eventually lead to the increase in the amount of reactants and therefore help the forward reaction. Adding inert gas doesn't do anything. All secondary cells are rechargeable. Yes. Yes. So all secondary cells can act as either galvanic or electrolytic cells. Yes. The polarity of the cathode during discharging is different to the polarity of the cathode during recharging. Yeah, so obviously cathode reduction, right? So reduction occurs at the cathode always. Okay. However, um, you know, the the cathode is here during recharge and during discharge, but then it's here during recharge. So this is recharge. This is discharge. So it'd be 1, 2, and 3. Okay. So obviously all secondary cells are rechargeable. That's its differentiating factor between primary and secondary cells. Secondary cells act as galvanic cells during discharge. So during the conversion of chemical to electrical energy, and then electrolytic cells from electrical to chemical energy. Um, Which of the following it represents the time needed to produce 2 moles of aluminum using a current of 7 amps. So they've just basically written out the equation for us, which is great. So we need to figure out the amount of time. So, okay, so the what is it? The C is equal to we do IT over 96. Forgot how to do it. So okay, cool. So what we want to do, I'm gonna work backwards here because I kind of forgot how to do it. But basically, we want to produce 2 moles of aluminum, right? So aluminum is like something like this. All I really want to get out of this is that there's a 1 to 3 ratio, right? So we want to produce 6 moles of electrons, right? Which means it would be 2 times 3, right? So that's 6 moles of electrons times by 96,500, right? And that C value is also relevant to I times T. So that is equal to 2 times 3 times 96,500. And then we want to find out T. So we just divided by the amount of amps, which is 7 amps. Sorry, I kind of forgot how to do it. But yeah, I think that sounds right. So F equals to IT or something. And yeah, or like the Faraday's charge. I forgot what to put here. Is it C or something? Forgot. But yeah, so it should be T equals to 2 times 3 times 96,500 divided by 7, which is A. Um, yeah. Cool. So, yeah, don't need to look at this too much because this reaction is going to stay the same. But we want to produce 2 moles, so that's 2 moles, and then we times it by 3, right? So there's a 1 to 3, so it'd be 6 moles that we do using. And to get the amount of Faraday charge or the Coulomb's constant required, we do 6 times 96,500 and then divided by 7. Yeah. So that was an easy question. I just kind of tripped up there. Bonds using carbon valence electrons have the same bond energy for all bonds. Carbon is the only element in the periodic table. No, silicon does as well. Tetrafluoromethane has stronger covalent bonds than tetrachloromethane. Um, okay, so yeah, so I'm not too sure how to do this question. I didn't realize this was on the study design, so I might have missed something. Um, Definitely know that B is not correct because they don't have the same bond energy. Um, yeah, it's a good one to just double check. I'm not too sure though. Yeah. Yeah, so sorry about that. I don't really know how to do that one, but let's keep going. Maybe somebody in the comments can let us know. So blah 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 blah. So this is basically 2-methyl heptane is basically a branched version of octane. So obviously it's going to have a harder time packing with the molecules, therefore leading to a lower melting and boiling point. So it should be A. Okay. So if you can imagine, it's much easier to stack something like that and therefore increases the amount of intermolecular forces. Okay. Because then it means that the amount of energy required to disrupt these forces is actually higher. But now suddenly you create a kink, or not a kink, but a branch. It's much harder to pack these molecules, right? And so then therefore the it's yeah, it's degree of dispersion forces actually decreases, right? And therefore reduces both its melting and boiling point. Is there much difference between the melting point and boiling point? No, not really. 2,5-dimethyl heptathrene. So you want to find we want to find the longest carbon chain. So if that's so there's a carbon double bond here at number 3. So then that's 3, that's 2, that's 1, 4, 5, 6. Sorry, the longest carbon chain isn't 7 carbons, that's 6 carbons. That's wrong. 1, 2, 3, 4, 5, 6, 7. Off to a good start so far. There's a double bond at that third carbon, which is good. And then there's 1, 2, 3, 4, 4, and then there's a methyl group at carbons 2. And then 3, 4, 5. So there should be another methyl group at that fifth carbon, which there isn't. It's at the sixth carbon, so that's wrong. This is 7 carbons, and then there's 2 methyl groups here, which means there will be 2 carbons there. So it should all together be 9 carbons. And that's 8 carbons, so that's not right either. So it must be that one. So I always go for like the structural formulas right first. I do all the easy stuff, so that's super easy to figure out that that should be 9 carbons there. So then it should be A. Cool. So you just want to do C, 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 C. Doesn't really matter, C. So 3, 6 carbons. So it should be hexane. So not that. Cool. So you find the longest carbon chain, which is 6 carbons. So even if I put my carbon there, it'd still be 6 carbons. And then you want to attribute the lowest, the lowest. So you basically, so the only thing here is that one says hexane 4 and one says hexane 3 ol. The only thing you have to consider here is if it's 1, 2, 3, 4, 5, 6, and then it's 1, 2, 3, 4, 5, 6. You want the hydroxyl group, which takes priority in this situation, to have the lowest number, which is 3 in this situation. So it'd be hexane 3ol. Cool. These are super easy. So pentan 1ol. So it's a secondary alcohol. This is such an easy exam. So pentan 1ol. So we want a secondary alcohol. So secondary alcohol, it's basically the definition of it. Please write this down if you guys don't know this. It's that the the carbon that's connected to the hydroxyl group, if it's only connected to one carbon, then it's a primary alcohol. If it's connected to two, it's secondary. If it's connected to three, it's tertiary. So we want something that's connected to 2 carbons. And we can see here that pentan 1ol and 5ol, they're both at the ends of the chains, right? Because there's 5 carbons in pentanol, right? So if it's at the end of the carbon chain, then there'd be then the carbon, right? So I'm going to quickly draw it out. Can you guys see how, because it's at the end of the chain, that carbon that's connected to the hydroxyl group, it's only connected to one carbon, right? Directly. And so therefore these two are wrong. Okay. And then let's try these other ones. So we've got 3-methylbutane 2-ol. So if we put that's there, and then that's there, right? So that one, number C, is right because we can see that it's a secondary alcohol because the carbon that's connected to the hydroxyl group is connected to 2 other carbons, and a methyl group is here. The reason why D is wrong is because it's saying that there's a methyl group here as well. Now, if there's a methyl group there as well, right, at number 2, then what's going to happen? Well, it means that the carbon that's connected to the hydroxyl group is actually connected to 3 carbons, which means it's a tertiary alcohol. Um, yeah, it definitely could have been harder. Let's see how we're going. So chemical J, one molecule of chemical J and one molecule of ethene can undergo an addition reaction to form a new molecule. Which one of the following could be chemical J? So the one that comes to mind normally is ethene and water, right? To form ethanol. But water is not one of the ones here. So ethene, so the reason why ethene would undergo an addition reaction is because we want something that can actually break up that double bond. Now, generally speaking, ethene could react with oxygen. However, it wouldn't go through an addition reaction. That would be a combustion reaction. So it wouldn't be B. We want an addition reaction. Ethane, I don't think it really necessarily reacts with it. And I don't think it really reacts with glycerol, right? Unless it reacts with its hydroxyl groups. But the double bonds and hydroxyl groups tend to not react with each other, but iodine does, right? So think about the iodine numbers we use to determine the how unsaturated a fatty acid is. The reason why is because we're exploiting iodine's ability to actually, turn the double bonds into single bonds. So it'd be C. Which one of the following is a possible product when a primary haloalkane reacts to produce a primary alcohol in a one-step reaction pathway? So say, for example, we've got something like Cl, and it's going to go give COH, okay? Basically, what happens is we give something like NaOH or KOH, and basically what happens is that OH basically substitutes, right? with the Cl, right? And then you end up forming something like KCl or NaCl, something like that. So you want something. Um, yeah, okay, so doesn't seem to have any of the stuff. So which one of the following is a possible product when a primary haloalkane produces primary alcohol? So let's see. None of these I'm happy with. So I've definitely done something wrong here. Why would it be Cl2? So the only way it'd be yeah, so it's not possible for it to be like ClOH or something, right? So it seems to be dealing with Cl. Hmm. Which one of the following is a product to produce is the following product when reduced to primary alcohol? So yeah, so we could have so I don't want to put water, right? Because what they're saying here is a H and a OH. And that OH substitutes with the Cl. And then what we end up forming is HCl. But we typically don't react a haloalkane with water. We just don't. Um, so it's not that. Definitely not KOH because that's what the reactant would be. It's not that. Hmm, an interesting one. Possible product. I think, out of all of these, the only, it's an interesting one. Yeah, so I'm not too sure. So water, I would say, is the most likely out of all of these, right? But yeah, typically water is used for addition reactions. But if we do it, then yeah, we can basically get water, HOH. I think that's the only one that's really likely here. So I'm just gonna guess. I think it's wrong, but yeah, we'll put the Cl with the H, so it might be B. I don't know about this question, so someone can maybe help us out in the comments. But yeah, I thought that water was generally only reserved for, yeah, yeah, generally it was only reserved for that, but that's okay. Cool. All right, let's keep going. When an excess of molecule G is added, it makes the color of the solution remain orange. So basically, this is already orange, right? Basically, yeah. So as we can tell, so from the data book, we know that when it's this solution, it's orange. Okay, so when this actually induces the oxidation of something else, right? It changes color, but it remained orange, which meant that this did not go through oxidation for some reason, right? And I think what they're basically trying to get at is what type of molecule does not go through oxidation. And as we know, there's primary alcohols, secondary alcohols, and tertiary alcohols. And out of those three types of alcohols, there's one alcohol that doesn't go through oxidation, right? Which is the reason as to why the solution remained orange and that it was not able to itself reduce because it did not induce the oxidation of molecule G. I know that's a mouthful, but this would only change color if it had successfully oxidized molecule G. So hopefully that makes sense. So we want to look at something that's a tertiary alcohol, and it looks like that one. So as you guys can see, you basically want to look at a compound that has a methyl group at the same carbon at which a hydroxyl group is connected. Because then that would mean, okay, if I could just draw it out really quickly, that carbon is connected to the hydroxyl group, it's connected to three carbons. So this should be a tertiary alcohol. What green chemistry principle is most consistent with designing a pathway with a high atom economy? So if we want to have something that's high atom economy, right? We ideally want something that goes A plus B to C. Okay. Why? Because if we do have something like D, that's just going to waste, right? And we want to prevent that as much as possible. So we want to prevent waste. Okay. So that's a simple recall question. This one looks fun. Okay, so we've got 0.073. We've got 0.075 to produce paracetamol and ethanoic acid. What is the percentage yield? What is the mass? Okay. I think we might have to find like limiting reactants and things like that, perhaps. So the limiting reactant is this one in this situation because there's less. So we're going to use this one. Okay. So because there's a 1-to-1 molar ratio, we want to find out the molecule that's the limiting reactant. And because there's less of 4-amino phenol, we're going to use this to dictate our stoichiometry. So 0.073, which means that there's 0.073 moles of this produced. So the mass of paracetamol that's produced is, if I were to look at the calculator, 0.073 times by 151, it's 11.023. Oh, it's very far away. 11.023 grams. Now, we've only collected 60.7% of that, so that's just times it by 0.607. And that's about approximately 6.69, which we a not as hard as I thought it would be. Which one of the following statements is most correct? The production of chemicals from industrial waste is sustainable. I don't think so. Where the production of chemicals from industrial waste is sustainable. The enzymes are the only catalyst consistent with green chemistry principles. Okay, let's go from the bottom. Solvents made from fossil fuels are better for environments than solvents made from plant material. Well, that's obviously wrong. You know, I mean, you guys should straight away notice that they're saying fossil fuels are better, which would never be true. The aim of designing safer chemicals is to ensure that the chemicals do not readily break down. Not necessarily, right? So safety and efficiency or efficiency of the chemicals themselves are very unrelated. Enzymes are the only catalysts and consistent with the green chemistry principles. No. So enzymes are biological catalysts. So if this is catalysts, enzymes is a small subset of that. But you still have metal catalysts that can still be consistent with green chemistry principles. But then I also thought the production of chemicals, from industrial waste is sustainable. Yeah, so what we're doing is we're basically producing chemicals from the waste itself, and that is sustainable. Yes, sorry. It's like, for example, producing biodiesel from restaurant oil, right? So that is sustainable. Sorry, I misread that. Cool. So carbon double bonds. So as soon as you see carbon double bonds and carboxyl functional groups, respectively. Okay, sorry. Oh, wait, sorry. React with Okay, so for carbon double bonds, you always want to use bromine water. Okay, so it's A and B, so it's C and D. And then a carboxyl functional group is COOH. That tends to be an acid, and we always use sodium hydrogen carbonate for that. I forgot what you use lime water for. Maybe someone can remind me. But bromine water, so Br2, similar to I2, it kind of works. So it turns something from brown to colorless. And then obviously when we react sodium hydrogen carbonate with a solution, with an acidic solution, so a solution containing the carboxyl functional group, it of course begins to bubble. Okay, let's have a look at this one. Melting point determination of a sample. If a sample starts melting at 49, is not melted, then a sample is a mixture. Not necessarily. Okay. Um, that's like so the actual melting point, like it could still just be a pure compound, and then the because the melting point is like when it's fully melted. Uh, So yeah, it's definitely higher than 53. So the sample doesn't mean that it's a mixture. It's also a definitive statement. So I don't think that um uh, um, yeah, it is correct. Or maybe it is. If the melting point of a sample is lower than expected, then the sample is a mixture. Um, no, not necessarily. Um, yeah, I'm not too sure about this. I'm gonna quickly go back to my notes and then I'll come back. Yeah, okay. Sorry about that, guys. As you guys might be able to tell, my melting point determination definitely needs some revision. Obviously, it's new to the study design. Um, so I haven't had much practice on it, but yes, sorry. Take back everything I said before. Um, Pure compounds tend to have very small ranges of less than 3 degrees Celsius. So if it starts melting at 49 but not fully melted by 53, it's likely that it's a mixture because, of course, you add things to compounds in order to decrease its melting point, right, of the entire mixture. So that's something that's very readily done in like industrial electrolysis, right, where we are adding compounds just to help the overall efficiency of the electrolytic cell. If the melting point of a sample is lower than expected, then the sample is a mixture. Not really. It actually could just be that it's not what we're looking for. Um, because yeah, it should be sort of the sample, the melting point of a sample is lower than expected, and the sample is a mixture. Yeah, so I think I'd be inclined to agree with that. Um, because um, except it is a bit of a definitive statement. So I'm not too sure. It could either be this one or just this one. So it's either A or C. Maybe someone can, yeah, I'm not too sure about this one. Anyway, let's keep going. We'll come back to it later. Saturated with a okay, let's is just nice old some nice old volumetric analysis. Um, so I like to do it like this sometimes. It just helps me. Right, so that's basically what's happening, I think. Or it's titrated with, oh, sorry, it's the other way around. All over the shop today. But anyway, that's one way to visualize it. So just put it the other way around. But anyway, let's just do it in terms of its actual thing. So we've got 10 mils saturated with that. So pretty easy. You just want to find out moles, which is just volume. So 0.01 times 0.882. So that's moles of H2O2. And you want to find out the moles of MnO4 minus, right? So we're reacting with this. So and there's a molar ratio of 2 over 5. So moles of MnO5, MnO4 minus, is 2 over 5 times 0.01 times 0.882. And then the volume would be, so we're trying to find the volume, would just be, so it's N equals to CV. Per liters. Yep. So it'd be V equals to N over C. Anyway, we'll figure that out part later, but let's figure out the moles first. So 0.4 times 0.01 times 0.01 times 0.882. So that's 0.003528. So that's the amount of moles of MnO4 minus. Um, and then you just divide that by the concentration, which is 0.1. And then just times it by 1,000, and you should get 35.28. Yep, that's pretty easy. But yeah, cool. And then you do 2 over 5 because it's, yeah, so there's 2 moles to 5 moles. So you get the moles, and then because you want to find out the mole and then the volume, it would just be volume equals to that. So that is that divided by the concentration, which has been given here. Should be 0.003528 over 0.1. And you times it by 1,000, right? Because that would give you 2 in liters. Okay, and then you want to times it by 1,000. So that should be that. Which one of the following sets of wave numbers is most consistent? So, oh, this one looks annoying. So you've got a carboxyl group, and you've got a NH group. So you've got carboxyl and you've got that. So that one tends to stay around 1600 to 1700. So it looks like something like that. Oh, but then there's that there. Okay, let's go to item 22 in the data book. IR. Oh, okay, because it's in terms of. So this is in terms of what? The carboxyl group is part of what? Would we say it's in. Oh, because. Oh, yeah. So this C. Oh, okay, that's interesting. So that's part. So that's an amide group, which means that carboxyl group would be part of an amide, which means it'd be from 1630 to 1680. So it'd be either these two. So it'd be these two. So one would be B or A. And then that amine group, so that NH would also be part of 3300, 3500. That's not there. It's very interesting. So that's a wave number is consistent with that, right? I've got item 22. So definitely 1630 and 1680. I wonder if they're just referring to the CH bond. So there's also a CH bond that we've forgotten about. And that would be from 2850 to 3090. Is there an RH group that I'm forgetting about? Um, um, so 1660. Mm, so it's wave numbers. Okay, so I think because they're all in the range, what they're trying to basically get at is how does the wave numbers of the carboxyl group itself, so they're not actually focusing on the NH. What they're trying to get at is when it's like this, what is it part of? And it's actually part of, if we were to just take CH3, CO, CH2, that carboxyl group is basically in of itself present in the compound as a ketone. And that there, it's present as an amide, right? So when it's part of the ketone, it'd be 1680 to 1700. Um, um, it'd be from 1680 to 700. So maybe something like that. Then. Yeah, I'm not too sure. Yeah, so it'd be 1680 to 1700. So most likely something like D. Okay, so I take back, yeah, I take back what I said about this um exam being easy. It's not the easiest. So there's three peaks, a quartet. Um, so there's a quartet there, there's a singlet there, and there's a doublet there. I have a feeling. Oh, so there's three environments there. There's three environments there. I wonder if there's three environments there. Hmm. Okay, so I wonder what the best way to do this. But like, yeah, so basically what they're trying to say is that so there's an environment here. The neighboring environment will have three hydrogens. Let's see how to go with this one. So CH. Um, so I hate H them all. But so that neighboring environment has so so that hydroxyl group is probably that. And then that So, and this environment actually has 6 hydrogens as its neighboring environment. So there should be a septet there, so it can't be that one. Um, yeah, and then so here, CH3, so there'll be a triplet and then a quartet. So there should be a triplet to represent that there's 2 hydrogens here in its neighboring environment. I don't think we've been given a triplet, so it's not B either. Here, we should also have a triplet there, but we don't, to represent that that the neighboring hydrogen environment has 2 hydrogens, but we don't, so it's not C either. I'm not convinced that it's this one either. Okay, so there's 3 environments, and so this environment would have a doublet to represent though because it's n plus 1 by the way. So a doublet would indicate that there's only 1 hydrogen in the name environment, which we do have. This environment would have a quartet to represent the 3 hydrogens in the same environment, which we do have. And this environment would represent the singlet to represent that there's no hydrogens in its neighboring environment. So it's the yeah, so don't try and refer to yeah, there's probably an easy way I could explain that. But yeah, don't try and refer to the data book. Just look at it in terms of environments. Um, calibration curve would be constructed by running solutions of the active ingredient. Okay, so here, what you want to do is you want to make sure that all other factors remain the same. So they're changing 2 things here, concentration and pressure. What you want to do is you want to keep the pressure the same. And then basically, in order to create the calibration curve, right, so that we can refer back to it, right, is we want to arrange different known concentrations, but at the same pressure. So it'd be B. There's no point in running the same concentration through at different pressures because you're not producing a calibration curve, right? So you want to know the concentration of an active ingredient. So what better way to find out and then to basically put a range of different known concentrations at the same pressure so that you can find out different absorbances. Victoria distilled this oil in a fractional distillation apparatus. So A, monitored the situation at the top of the fractionating column during the distillation process. At the end of the distillation, some liquid remained in the distilling flask. Which one of the following is true if the distillation produced a distillate of 80% pure apenine? Yes, so we've got 156 degrees, 176 degrees, and it's a fractional distillation process. Okay. So if we were able to produce about 80% pure apenine, then the melting point of the distillate was greater than 156 degrees Celsius. Not necessarily. So that's a pretty high, like we've got a pretty high percentage composition of pure apenine, right? So it doesn't necessarily mean that it's higher than 156 degrees Celsius. The temperature of the distillate collected in the receiving flask was 156 degrees Celsius, not necessarily as well, right? Because of course, like, we can't really control its temperature, right? And then it also gets condensed. Okay. The temperature of the liquid in the distilling flask was greater than 156 degrees Celsius during distillation. Yeah. So generally speaking, what you want to be happening is you've got something at 156, you've got something at 176, and you want to keep the temperature range in this area to make sure that we're not boiling our 1,8 cineol, right? So to ensure that this remains liquid, we want to keep the temperature range in this area, which means that the temperature of the liquid in the distilling flask was probably greater than 156 degrees Celsius during the distillation. Okay. And then the distillation was stopped as soon as the temperature at the top of the fractionated column reached 156. No, we wanted to reach somewhere in there. So basically, by having the temperature reach above 156, we can ensure that all of A pinene is a gas, and then we can basically condense it back into a liquid, and then it goes into the distillate. So that's easily C. Okay, so a calorimeter with a digital temperature probe was calibrated. A calorimeter was then used to measure the enthalpy of the chemical reaction. It shows the first six temperatures recorded in the first 5 minutes from when the reactants were mixed. The graph was used, by which one of the following would best improve the determination of the maximum temperature reached by the calorimeter. Cool. So basically what we don't have a sense of in this situation, right, are the sort of minute changes that happen of the temperature. Um, we don't really have. So, what could have been what I'm basically trying to say is in order to determine what the maximum temperature was, what we could be actually seeing, right, for all we know, is something like this, right? But we don't actually have that information. Why? Because we only took the temperatures at 1 minute intervals, right? So I'll just quickly repeat that. In order to best determine the maximum temperature, what we would have liked to do is we would have liked to take it every 5 seconds or 10 seconds or 2 seconds, right? Because then we would have been able to detect the minute temperature changes and then accurately detect when it reaches its maximum temperature, right? Because here it says it's at 3 minutes, but we don't know that for sure. All we know, right? For example, for example, it could have gone something like this and then reached it, and then that would be the maximum temperature. So actually recording the temperature every 20 seconds, okay, would allow us to know what the maximum temperature is. So question number 30, which one of the following statements take that identified mistakes should not be included in the subsequent data analysis or reporting? Yeah, so if you've already identified the mistakes, yes, these are mistakes that are identified. Generally speaking, you don't really include it in the data analysis and reporting. There's no really need for it. An outlier in an otherwise highly precise set of feature measurements indicates a systematic error. So generally speaking, no. If we have like one or two outliers, then it means that it'd be more so because of a random error, right? So something that happened specific to that situation in which it caused it to be an outlier. And so therefore one is correct, but I don't think two is, it'd be A. Cool. So not a bad exam. Again, with that question here, maybe someone can help explain this question number 23, but I think the rest of it was very, very chill. Oh, and this one was also really weird. So I had a couple of weird ones in there. Maybe it's from past my time, but overall, a very easy exam. Okay, cool. Let me know if you have any questions. I know some of this was choppy, but hopefully it was okay. See you later.